welcome to another exciting video on the Science Lab YouTube channel. Today I am going to be looking at equilibrium of three forces acting at a point, and I'm going to try as much as possible to find solution to some examples using up to about 3 different methods, so that you understand at the basis on how to solve problems on this. So the 3 methods are the triangle of force method, 2 resolution of forces, and 3 scale drawing method. I'll try as much as possible to use 1 or 2 or more of the example the methods here to solve 3 examples where possible, if I can use the 3 methods. So let's quickly roll over and see the problems that we have before us. So this is the first problem I have here. A mass of 2.0 kilogram is supported by 2 cords, which makes angles of 30 degrees and 50 degrees with the vertical. Calculate the tension in the 2 cords. So what I'm going to do is this. I'm going to represent this on force diagrams, then we use triangle of forces, and again we use resolution, and again we use the scale drawing method. So let's go through the question again. A mass of 2.0 kilogram is supported by 2 cords which makes angles of 30 degrees and 50 degrees with the vertical. Calculate the tension in the 2 cords. Obviously, because the cords are making different angles with the vertical, then the tensions in the cords are going to be different. So for this problem, I'm going to be using G equals 10 meters per second square. So that is the value I'm going to use for the acceleration due to gravity. So let's quickly get into business and let's see this. So the mass of the object is 2.0 kilogram. So first of all, let me draw this. I'm going to draw an object. Okay, let me just use a simple diagram like this. So the mass is 2 kilogram. The weight of the object is going to be 2 times 10, that is 20 Newton. Remember, I said I'll be using 20 Newton for my acceleration due to gravity. Now let's take a look at this. So if I have 20 Newton, then it's supported by 2 cords, which makes angle of 30 degrees and 50 degrees with a vertical. So if I have a fixed point here, this represents a fixed point. I have a chord here, so the chord makes an angle of 30 degrees with a vertical. So this is the vertical, this is horizontal, and this is vertical, 30 degrees. So the tension, let me call the tension on this chord as T1. Then I'll represent the other chord, T2, which makes an angle of 50 degrees with a vertical. So I'm going to draw this. This is my vertical. So it makes an angle of 50 degrees with a vertical. So I'll use the triangle of force method as my method 1. So for method 1, so since I'm using the triangle of force method, triangle of force method is actually the most easiest method to use. Why did I say that? If I'm using the triangle of force method and I can analyze and get my result, I can also use the triangle of force method to draw scale diagram to get my result. So what I'm going to do is this. This is the vertical force acting in all of this system, the weight of the object. So I'll draw a vertical line like this. So this is going to represent the weight, 20 Newton. And the next thing I have to do, so the weight is going to act definitely in this direction, even though we don't actually need the direction, because we just require the magnitude of the tension T1, and okay, this is going to be T2. Okay, then let's look at this. T1 makes an angle of 30 degrees with the vertical. So what I'm going to do is this. I'm going to draw T1 along this line, making an angle of 30 degrees with this vertical line. So this is T1, making an angle of 30 degrees with the vertical. Then T2 making an angle of 50 degrees with the vertical on the other side. So this is 50 degrees, and this is my T2. So what I have to do is to look for this angle here. So let me call this angle theta. So angle theta is going to be 180 degrees minus 50 plus 30 degrees. 50 plus 30 degrees is 80. 180. So theta is going to be 180 degrees minus 80 degrees, which is 100 degrees. So I have found what my theta is. My theta is 100 degrees. So the next thing I have to do is to apply sine rule. So since I know this angle here, I think we should tell the reason why this is this. So sum of angles in a triangle. So we know this. That's why we did this, because the sum of all these angles should equal 180. They are all supplementary what angles. So by applying sine rule, I'm going to have sine theta. Theta is 100 degrees. Sine 100 degrees divided by the side opposite it, which is 20, is equal to sine 50 degrees divided by the side opposite it, which is T1, is equal to sine 30 degrees divided by the side which is opposite it, T2. So from here I can easily calculate my T1 and T2. So this is going to be my T1. So from here I equate this to this. So I have sine 100 degrees divided by 20 equals sine 50 degrees divided by T1. So when I cross multiply, I'm going to have T1 sine 100 degrees equals 20 sine 50 degrees. So my T1 is going to be equal to 20 sine 50 degrees divided by sine 100 degrees. I'm going to press this for my calculator. So I have 20 sine 50 divided by sine 100. So that's going to give me 15.55 or 15.56 Newton. 15.56 Newton. So that gives me T1. Now let me calculate T2 on this other side. So I'm going to have this. Let me just calculate T2 here. So I'm going to have T2. Again, I'm going to equate this to T2. So I have sine 100 degrees all over 20 equals, I'm equating this to this, sine 30 divided by T2. So on cross multiply, I'm going to have T2 sine 100 degrees equals 20 sine 30 degrees. So my T2 is going to be 20 sine 30 degrees divided by sine 100 degrees. So I'll press on my calculator. 20 times sine 30 degrees divided by sine 100 is equal to 10.15 Newton. So these are the magnitudes. This 15.56 and 10.15 Newton are the magnitudes of tension T1, tension T1 and T2. Now, I'm going to flip it back and use resolution of vectors to solve for this again. Then I will use K diagram to solve for it. Now, in using resolution of vector, I'm going to draw a free body diagram for our mass. This was my mass. I'm just going to replace it with a simple dot. So I'll place a dot here. Then I'll draw the weight. Use an arrow to represent the weight. This is 20 Newton from our previous calculation. Then from this, I'm going to have this. And the other vector of force. So this is T1 and this is T2. Remember, their forces, their angles are to the vertical. This is 30 degrees and this is, okay, let me take this off here, 50 degrees, and I'll take this as T2. Now I'll just resolve the forces to the vertical or horizontal direction. How do I resolve the forces? I'm going to have this. Now, let me complete this as a triangle or as triangles. Let me draw this way, and I'll draw this way. So I'm going to have this. So these lines are not straight. These are vertical lines. Vertical lines. Now look at this. If I call this place O, and let's call this A, B, and this is C, D. We have two triangles. Now by applying SOHCAHTOA, I'm going to have this trigonometry ratio, because this is a right angle and this is a right angle. So for this triangle AOB, this is going to be the opposite and this is going to be the adjacent, while this is going to be the hypotenuse. For this triangle OCD, this is going to be the opposite, this is the adjacent, and this is the what? Hypotenuse. So once you do this, what I intend to do is to get the vertical magnitude of these forces, to get the vertical component of these forces, T2 at this component and T1 on this component. So I will be ignoring this and this. Now in this case, I will need that when I want to resolve for the horizontal component. So I am resolving for the vertical component, sum of forces in the vertical direction, y direction, this direction please. So I'm going to have this. So if I apply the sine rule or SOHCAHTOA, your SOHCAHTOA is this. So sine is opposite over hypotenuse, and your cosine is equal to adjacent over hypotenuse. So I will leave it at these 2 points. I will not be using the TOA. So now let's look at this. This is adjacent and this is hypotenuse. So it means that if I want to get this, I'm going to use cos 30 degrees. Cos 30 degrees is equal to adjacent or adjacent divided by the hypotenuse. So obviously you find out that the adjacent is equal to hypotenuse times cos 30 degrees. So that will also apply with this. So it means that the component of this force, the hypotenuse is T1. So it means that the component of this force T1 in this direction is going to be T1 cos 30 degrees. Also, the component of this force T2 in this direction is going to be T2 cos 50 degrees. Then we already have this in this direction. So we see that we have the vertical component of the forces now, which are T1 cos 30 degrees and T2 cos 30 degrees. So the sum of the vertical forces will take the forces from the 0 point upward to be positive and this to be what? Negative. So on doing that, so I'm going to have, so the positive forces are T1 cos 30 degrees plus T2 cos 50 degrees minus 20. So I'm taking this to be negative because it's downward, equal to 0. Of course, the system is in equilibrium. So the sum of all the forces must be equal to 0. So by doing this, I can say T1 cos 30 degrees plus T2 cos 50 degrees equals 20. So I call this equation 1. Now notice that we have two unknown values here, forces here, T1 and T2. So it therefore means that we must look for another equation. We have to derive two equations to be able to solve this. So how do I do that? So let me resolve this force in the horizontal direction. So sum of forces in the horizontal direction. Now let me go back to this, what I did here. So I have to do it for sine. Now sine theta is opposite over hypotenuse. If sine theta is opposite over hypotenuse, go to this triangle. See, this is opposite. So I'm looking for the opposite side. So it therefore means that the opposite is going to be equal to hypotenuse times sine theta. Can we get this now? How do I do that? Just cross multiply and bring this here. So the opposite is equal to this. So the component of this vector T1 in this direction is going to be T1 sine 30 degrees, and the component of this vector in the horizontal direction is going to be T2 sine 50 degrees. Now we take this side to be positive and this side to be what? Negative. So this is going to be negative and this is going to be what? Positive. Now let's take the sum of all the forces. So I have T2 is positive, T2 sine 50 degrees minus, because this is negative, T1 sine 30 degrees equals, because these are the only forces acting in this direction and this, there are no other forces. So of course it's in equilibrium, then it must be, the sum must be equal to what? 0. So from here, what do we do? From here, I'm going to make T2 the subject of the formula, meaning that my T2 is going to be equal to, just shift this way, becomes T1 sine 30 degrees divided by sine 50 degrees. That's T2. So what do you think I should do? This is equation 2. So I'm going to substitute T2 into, or substitute for T2 in equation 1. So I'm just going to replace this with T2 wherever I find T2 here. So it means that I'm going to have, so from this equation 1, this was my equation 1. From equation 1, I'm going to have T1 cos 30 degrees plus, now instead of T2, my T2 is going to be this T1 sine 30 degrees divided by sine 50 degrees. Are we following? Times cos 50 degrees equals 20. So I'm going to press my calculator from all of this. Cos 30 degrees is going to be equal to 0.866 T1 plus, let me just work this out. I'll do sine 30, that's 0.2, sine 30 times cos, sine 30 times cos, sine 30 times cos 50 divided by sine 50. That's going to give me 0.4195 to 4 decimal places T1 equals 20. So I can add this together. So I have 0.866 plus 0.866 plus 0.4195. That gives me 1.2855 T1 equals 20. So T1 is going to be equal to 20 divided by 1.2855. 20 divided by 1.2855. That gives me 15.56 Newton. I think this is familiar to the previous result that we got. So here we can just substitute for T1 in equation 2, T1 in equation 2 to get T2. So let me just do that all over this place. So my T2 from here is going to be equal to T1 is 15.56 sine 30 degrees divided by sine 50 degrees. So my T2 is going to be equal to 15.56 times sine 30 divided by sine 50. So I'm going to have 10.17 Newton to 2 decimal places. Now you can see that our result is familiar with that. Let me just flip and check the other results. So these are the comparison between the first method and the second method. So you choose which of the method you prefer. So the next thing I'm going to do is to use the scale drawing method to get the values of T1 and T2. So in the scale drawing method, all I need is a protractor and a ruler. So we are going to choose an appropriate scale. Remember that the weight of our force was, of our mass was, or the object was 20 Newton. So I'm going to choose an appropriate scale for that. I think I should be choosing, okay. So I can choose a scale of, let's say, 1 cm to 5 Newton. So if I choose a scale of 1 cm to 5 Newton, I'm going to have 1, 2, 3, 4. 4 times 5 is 20. So let me choose my scale. Scale 1 cm to 5 Newton. So here I'm going to come to this place. Okay, first of all, I need to get a right angle triangle. Let me draw a vertical, horizontal line. So I have a horizontal line, and I am making this, okay, this point my center. So I have to get a 90 degrees from this. So placing this on this, I get my 90 degrees. So from this, since I have a scale of 1 cm to 5 Newton, I'm going to measure 4 cm from this. So this is 4 cm, 4 cm. So this is my 4 cm. Okay, we may not even be needing the horizontal line anyway. So I have 4 cm. Then we now go back again. This makes an angle of, the first makes an angle of 30 degrees with the vertical, and the other with 50 degrees with the vertical. So I'm going to do this. Whatever point you want to start from, let me measure 30 degrees from this line. I'm going to measure 30 degrees from this line. So I have this is, okay, let me turn this. So I have this is 90, so I'm going to take 30 degrees this way. So I'm going to end at 60 degrees. That's 30 degrees. So I'll draw a straight line through this from this point. Draw it to any end. Then come to the other side. Then I'm going to, it makes an angle of 50 degrees. So here I'm going to measure 50 degrees. So this is, so I'm drawing it from this point. This is my 4 cm, the end of my 4 cm. So I'll place this on this. Then I'll measure 50 degrees from 90. So when I go, this is 10, 20, 30, 40, 50. So at this point here, so I'm going to draw a straight line through this. Just draw it to any length. So that's okay. So what we need to do, you can measure this angle over here. You can measure this angle over here by placing this. Okay. Okay, let me place this on this so that I can measure it from this line. Though we do not need the angle actually. So this angle is going to be 0. This is 100 degrees. So it is 100 degrees. If you trace this upward like this, it's going to be on this point. So what you need to do is to measure the length of this. So the length of this is 3.1 cm. So this is my T1 and this is my T2. So T1, the length of T1 is 3.1 cm. Remember, our conversion scale is 1 cm to 5 newton. So I've just multiplied that by 5. 3.1 times 5, that gives me 15.5 cm. So T1 is actually going to be equal to 15.5 newton, which is close to what we had there. Then you come to this place, measure the length of this, and that's going to give me 2.1 cm. So T2 is equals to 2.1 cm. So my scale, my conversion scale is 5 newton. So I've multiplied 2.1 times 5, and that gives me 10.5. So my T2 is actually 10.5 Newton. Now, bearing all other measurement errors, you'll find out that in all three methods, our results are very close to each other. Our results are very close. You can see this was the method of triangle of forces. So these are the forces that we had. And for the method of resolution of forces, we had 15.56 and 10.17, which is relatively close to what we had here. So that will be all I can take on this video for today. See you in our next video. Do not forget to hit the subscribe button and also like this video and also share so that other learners can get a grip of what we are doing here. Thank you very much. See you some other time.